So now that we know how to calculate capacitance for all sorts of interesting things, now we're going to say we're getting to the more practical side of things where we know we have these things which are manufactured, which are called capacitors, and their function is to. My screen just froze up for a second there, so I was nervous. All right, their function is to hold charge. So we now are just going to use what we know from the definitions of capacitance to try to determine how these capacitors act when they are together in a circuit. So we will find out, and we're going to do the same thing for a few different other circuit elements. Basically, you guys, even though we haven't done anything with circuits yet, you guys have a pretty good idea that it's probably very unlikely that there's any circuit where you just have one capacitor and a battery and that's it. You're going to have other things in there, including other capacitors. So what we're going to deal with right now is how do we treat a circuit that has multiple capacitors in it. And you'll see we can just use the very standard rules that we already have. I just see that I've chipped the glass in this corner already, so I need to do something with this. I need to talk to the producer of the Posh Studios here. Okay, so what we are going to look at is something like this. What happens if we have? Oh, let's do this one first. Sure. What the heck? Your book does this one first. We'll go along. Okay. Okay, so we've got this. So you will recall this is a battery, and this is the plus V side, the bigger one, and this is the minus V side, which we're just calling 0, so we're just going to say V. Normally this 0 is not written, and a lot of times you won't even write this V. You'll just look at this and you'll know it's a battery, therefore it has some voltage V. Okay, so you will recall, however, that anywhere along a conductor is going to have the same voltage. So this voltage V is the same as I have right here, same as I have right here, same as I have right here. Okay, meanwhile, of course, I have 0 here, 0 here, 0 here, and that is because there is nothing but conductor between here and the battery. Remember, if that's not true, then that also, excuse me. If it's not true that there's just conductor here, it will also not be true that this voltage is the same as this voltage. Remember that. That will be important when you get to later stages. Okay. However, because there is nothing there, we know this V, so our voltage difference across each of these capacitors is V. Meanwhile, what's our capacitance? Well, we're just going to call it C1, C2, C3. I just realized the top of this might not be, so I'm just going to pull this down once so you can take a peek at that and see what circuit we're dealing with, just in case it's not showing on your screen, which I cannot see right at the moment. Okay. So, that's our circuit. Now, what are we doing? Oh, now what we're trying to do is this. We're looking at this and we're saying, gosh, we have 3 capacitors now. We know how to deal with 1. How the heck do we deal with 3? And the question and what we'd like to do is make this dealing with 3 as if we were dealing with just 1. So I had my definition of capacitance wrong, which is why I stopped this and restarted it, because it took me, I don't know, 45 seconds to remember the right one. I didn't want to waste your time. Okay, so what Q is on each of these? So we just have some Q on each of these. I'll go ahead and label it Q1, Q2, Q3. Doesn't matter that much, but okay, so what's the Q? Well, we know the definition of capacitance is just C equals Q over V, and so if we want to know what charge this is, it's just CV. So, what is the C here? It's C1, so that's 1 bit of charge here. What's the second bit of charge? Q2 is just C2, and once again, the V is the same. Therefore, we can keep it like that, and then we have C3V. And what does this equal? This equals Q total, QT. Yes, okay, so this equals the total charge. Well, we want to determine, I'm going to move this out of your view now that you've all seen that. probably move it out of view. I don't know if it's going to still be on the screen or not. Ooh. Okay. So, so what's our job? Now we're going to use this right here to determine what our equivalent capacitance is. In other words, what one capacitor would hold exactly the same amount of charge. Well, we're just going to use this definition, Q total over voltage. I'll go ahead and say equivalent. We could also say total capacitance, but equivalent is the standard terminology. So the C equivalent for this would be whatever this total charge is divided by the voltage. Okay, just by definition. So we're just going to substitute in what this is. We have C1V plus C2V plus C3V divided by V. And so our equivalent is just C1 plus C2 plus C3. So this configuration here, we call this a parallel configuration. And what that means is once I just realized we haven't really talked about current. I really don't like the fact that your book does this chapter before it does the next chapter, but it doesn't matter. We're sticking with it. So the current, the charge, the moving charge, when it gets to this point, when it leaves here, how many paths does it have to go by? Just one, just one. There's only one spot for it to go. Anything that is along this one path, we say it's in series, which means there is only one path for the charge to move. However, once there are separate paths for the charge to go on, we call this in parallel. And so these separate paths for in parallel, we just define this as a parallel configuration. So so I'll just say capacitors, caps in parallel, this is the equivalent. And you can see quite easily that this would be, plus, 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 however many capacitors you had in parallel. All right, that's how you add up capacitors in parallel.